Alright, welcome to video number 2 for uniform circular motion and centripetal acceleration. Hopefully my voice is a little bit louder this time. I've upped the microphone levels. We started talking a little bit at the end of last class about what things might affect the acceleration of the object. And it was pretty well understood that there are two things that affect the acceleration of the object as we go around in a circle. So let's take a look. Say we have an object going around in a circle like this of radius 3 meters. And it's moving around in this direction, in the counterclockwise direction. That means that at every point we can tell what the velocity is. The velocity will be in red here. The velocity is tangent to our circle and should be approximately equal in size all over the place, although I know that I didn't draw that perfectly correctly. And also we have our acceleration, which draws directly in toward the center. So the blue lines here are our acceleration. And so as we see our acceleration pulling in toward the center and our velocity tangent to the curve, we know that our acceleration only changes the direction of our velocity. As we saw last time, the acceleration is not changing at all the speed that we go around at. So the magnitude of velocity is constant in uniform circular motion. So that means that our acceleration depends on just the change in direction of our velocity, or rather, the size of our acceleration dictates how big our velocity changes its direction. Remember that acceleration's magnitude is given by the change in velocity over the change in time. So there are really two things that can affect the magnitude of our object's velocity: how big the change in velocity is and how long it takes for it to change its velocity. So the two things that will affect indirectly then acceleration, because they will affect both delta v and delta t, are the object's velocity, obviously, and the size of our circle, the radius of the circle. We're going to start with looking at how the radius of our circle affects our acceleration, and we're going to take a look at two circles. So here's one circle, and here is a second circle of a much bigger radius. Now, you can imagine that if I were looking to change my velocity from here to here, let's say this is 5 meters per second here, and this is negative 5 meters per second here. This would take t over 2, half of our time period, to change that, right? So the time it takes to change from 5 meters per second to negative 5 meters per second is half of our time period, half of our period t. If we're traveling at the same speed over here, 5 meters per second here, and then negative 5 meters per second here, we can see that because this radius is much bigger and because velocity equals 2 pi times our radius divided by our time period, the bigger the radius of the circle, the bigger the time period. So even though here our time is still capital T over 2, I'm going to call this one T1 and this one T2. T2 is much bigger than T1, so therefore the time it takes for this one is greater than the time it takes for this one, right? So if we call this T2 and T1. And so now we see that, remember, acceleration is delta v over delta t. The delta v is the same. It goes from 5 to negative 5 in both cases. But the time it takes in this case over here, case number 2, compared to case number 1, is much longer. And so as a result of our denominator being much bigger, the acceleration for number 2 is less than our acceleration for number 1. Right, because the bigger that the delta t in the denominator gets, the smaller our overall acceleration is. So we know that acceleration then is directly proportional to the inverse of our radius, right? Or it's inversely proportional to our radius. That means that as our radius gets bigger, our acceleration must get smaller. Now, in terms of the velocity, let's imagine two situations of circles with equal radii. So So here's our two situations of circles with equal radii. And let's imagine that over here our magnitude of velocity is 5 meters per second. And over here our magnitude of velocity is 10 meters per second. Now first, we know that if we are thinking about these two locations that we thought of before, directly to the east and directly to the west, that our delta V on the right-hand side is going to be bigger, right? Because here it's going 10 meters per second, and then here it's going negative 10 meters per second, and then here it's going 5 meters per second, and here it's going negative 5 meters per second. So not only is, remember acceleration is delta V over delta T, not only is delta V equal to negative 20 here, and delta V equal to negative 10 here. But think about what else is going on. As we're traveling at a higher speed in the same radius circle, our time period T2 here for going around one revolution, T2 is going to be less than T1. So not only am I going to increase my delta V, the magnitude of my delta V, but I'm also going to decrease the magnitude of delta T. And so the result is that acceleration here, acceleration 2, is not just greater, but is in fact much greater than our acceleration in situation number 1. So that tells us that acceleration is at least directly proportional to velocity. And in fact, what we'll find, because there are two factors that are changing, it's directly proportional to velocity squared. It's directly proportional to velocity squared. And so the result is that we get an equation for our acceleration when we're going around in a circle as the following. Our centripetal acceleration, the acceleration, the amount of acceleration that's pulling us in toward the center of our circle, is equal to v squared over r, where v is our velocity or our speed, magnitude of the velocity or the speed, and r is the radius of the circle. And now we can see how this directly relates to the force, because if we remember Newton's second law, which says that the net force on an object is equal to its mass times the acceleration, that means that anything that's going around in a circle will have a net force on it equal to the mass times the centripetal acceleration. And we just found our centripetal acceleration was equal to v squared over r. So our net force on an object going around in a circle, the amount of force required to keep it going in a circle, is equal to mv squared over r. Now, there's a couple things to note. First off, this expression is only for uniform circular motion. I guess technically it's not uniform circular motion, but we'll only use it for uniform circular motion. So that's the first thing to think of, that we can only use this F net equals mv squared over r when we're going around in a circle, because that's the only time that our acceleration actually depends on both our velocity and our radius in this way. The other thing to realize is that this net force is not a new force. It's not a force that we can draw on our free body diagram. Just like before, when we had a force going to the right 5 newtons and a force going to the left 3 newtons, we would say that the net force, F net, was 2 newtons to the right, F net equals 2 newtons to the right. This green force here is not something that we would draw up here, because it's not an actual force. It's the difference between the winning and the losing forces. So that means that here, our F net is the difference between the winning and the losing forces. But we have to be careful, because what is going to be the winning force and what is going to be the losing force? Well, we always know what the direction of acceleration is. We always know that the direction of the acceleration when we go around in a circle is toward the inside. So here, our F net is equal to the forces that are winning minus the forces that are losing. But in this case, our forces that are winning are always our forces that are going inwards, and our forces that are losing are always our forces that are going outwards, because we always know that these inward forces have to be bigger than our outward forces because we are accelerating inward. Our acceleration is inward. So that means that whenever we are writing our F net expressions, we're always going to use our inside forces minus our outside forces. Now let's take a look at an example to make a little bit more sense of this. So let's imagine a yo-yo traveling in a circle of radius r. And let's imagine that the yo-yo is at the very bottom of its path. If I were to draw a free body diagram of this yo-yo, at the bottom of its path it would have a tension force from the string up, and it would have a gravity force of mg going down. Now I know that at the bottom of my yo-yo's path, my acceleration is up, so that means that tension must be greater than mg, or my weight force. So if I were to write my net force, I would say F net equals tension minus mg. But we also know that as we go around in a circle, tension minus mg is going to be equal to the mass times the acceleration, right? That's Newton's second law. But our acceleration is v squared over r. And so the result is our net force expression, whereas before it would have been something like ma equals t minus mg, here our net force expression is mv squared over r equals t minus mg. Oops. mg. And so then this part, the v squared over r, that's our acceleration as we go through this circle. So then this is really the same thing. ma equals t minus mg translates to, in a circle, mv squared over r equals t minus mg. And what's the use of this? Well, if I wanted to say know how big the tension force was at the bottom of the circle, I could, as long as I knew my velocity, and my radius, and the mass of the object. So let's try it. Let's say that this is a typical yo-yo, so the radius of this typical yo-yo is approximately 1 meter. We'll say that the mass of the yo-yo is approximately 200 grams, which is the same as 0.2 kilograms. And let's say that we are spinning it around at a speed of 3 meters per second. And I want to know two things. First, what is the tension at the bottom? And second, what is the tension at the top? So if I were to do a round-the-world spin, what is the tension at the bottom and what is the tension at the top? So go ahead and try to figure that out. Pause the video, try to figure that out, and see how it goes. And welcome back. So let's take a look. So we know that at the bottom, tension at the bottom, our free body diagram, again, looks like this. We have a tension force going up, we have an mg force going down, and we know that at the bottom, our acceleration is upward. So that means that this force is our winning force, and this force is our losing force. So F net is equal to tension minus mg. F net is mv squared over r as we go around in a circle, which is equal to tension minus mg. So at the bottom of our circle, we can say that tension is equal to mv squared over r plus mg. As I plug all that in, I've got 0.2 times 3 squared divided by 1 plus 0.2 times, for our sake, let's just say 10. So this is 0.2 times 19, or approximately 3.8 newtons. 3.8 newtons going up, and if we compare that to our weight, right, mg weight equals mg, our weight is 0.2 times 10, so our weight is then 2 newtons. So we said that the tension force has to win and our weight force has to lose. Well, tension force is 3.8 newtons and our weight force is 2 newtons. So we can see that yes, sorry, this is weight, not tension. We can see then that our tension force does in fact win. Now at the top of the circle, things get a little bit different. So our tension at the top, T top, our free body diagram looks a little different because at the top, our tension is pulling down and our weight force is pulling down, so mg pulls down as well. So at the top, our F net, both of those forces are in the same direction, and they are both inward, and our acceleration is inward again, which at this point means it is down. So that means that any forces going down are our winning forces. So our F net then is tension plus mg, and we're not going to subtract anything because there's nothing going in the opposite direction. So that means that mv squared over r equals tension plus mg. So therefore tension equals mv squared over r. Let's just fix that. mv squared over r minus mg. Before we found out that mv squared over r was 0.2 times 3 squared divided by 1. We're going to subtract away from that mg, which we found was 2 before. So this is 1.8 minus 2. And so this actually does not work very well for us because we end up with a tension which is negative. Now, a negative tension means that the cord actually slackened. So whenever we get a negative tension, that means that the cord actually went slack. It kind of bent a little bit. And that means that it didn't complete the circle. And we'll talk about how we figure out whether or not the object completes its circle later on in class. But we notice that the tension is negative 0.2 at the top, and the tension is 3.8 at the bottom. So we can see then that it is much less at the top than it is at the bottom. And that makes sense, right? Because at the bottom, the tension is responsible not only for overcoming the weight, but it's also responsible for accelerating inward. So it not only has to overcome the weight, but it also accelerates inward. At the top, it doesn't really matter. The weight can do that job. We'll be practicing a lot of these in class next time, so please come to class ready to take a look.